So in lecture 6 of the physical chemistry series, we're gonna expand on really thermodynamics as a whole, right? So the first thing we're gonna discuss is the idea of what is a system. And we say the system is a part of the world in which we have a particular interest, right? So this could be examples in the form of, a gas in a reaction flask. Right, so we could have a gas in a reaction flask. We'd also have maybe fuel. We'd also have maybe fuel air mixture in an engine. We could also have a battery, right? So these are various examples of what we call a system, right? Now, another term that we have to be mindful of in thermodynamics is the idea of the surroundings, right? And the surroundings is simple where we actually make It's actually where we make our observations. The surroundings are actually where we actually make our observations on the system itself. How about the universe? We've heard this term in thermodynamics before, but what does it exactly mean? Right? The universe is what we defined as the system plus your surroundings. Another term that we must also use in thermodynamics is the idea of what we actually call boundary, or in other words, walls. And this is actually what separates systems from surroundings. So this actually separates the system from surroundings. Right? And we have different types. So the type of wall determines the type of system. Right? So the type of wall determines the type of system. So let me write that down. The type, because that's important. The type of wall determines the type of system. So what are the type of systems that we have? The first one we're going to talk about is what we call an open system. And this is where energy and matter can flow between systems and surroundings, right? So this is where actually energy, both energy and matter, can flow between system and surroundings. Examples for this could be something like, an open flask, or something like a human being, right? The earth, a biological cell. These are all open systems, right? Again, we say energy can flow, and both energy and matter can flow between the system and the surrounding. So maybe if we take maybe a generic example and we say a box, this can be the system, and let's say everything around it is the surroundings. And the idea of an open system is that both energy, and this is energy, and then we have matter, they both can flow both in and out the system. So that's the idea of an open system. The second one that we're going to talk about is a closed system. And this is where energy can flow. So energy can flow between systems and surroundings. but matter cannot. So energy is free to flow, but matter cannot. First examples like this include maybe like a stoppered flask that you may use in a general chemistry lab, or a thermometer, right? And so if we do the representation for a closed system, we could say that, okay, well, we can say that maybe this is our system, and we have some sort of surroundings around it. So this is our surroundings. And the idea we're saying is that energy, I'm just going to write E for energy, can flow in freely between the system and the surroundings, while matter cannot. So I'm going to use M for matter, and we're saying that matter cannot. So that would be like a graphical representation of a closed system. The third one that we want to talk about is the idea of an isolated system. And this is where neither, right? So this is where neither energy nor matter can pass system walls. So this may include examples like, a stoppered insulated flask, or thermos, or even picnic coolers, right? So coolers that you use at a picnic, this is an example of an isolated system. And so if we do a kind of a graphical representation, okay, well, we may have the system right here, and everything around it is the surroundings. And what we're saying is that energy can flow in between between each. So I'm just going to use E for energy. And we're also saying that matter, represented by M, cannot flow between the system and the surroundings. Right? So those are the three types of system that we must keep in mind. You must know the difference between all three as a physical chemist. Right? Another term that we want to talk about is the idea of a process in thermodynamics. And a process is some kind of change in the system. So a process is some kind of change in the system. So an example may include like a change in a physical state, such as maybe compression, right? So examples may include a change in physical state, such as maybe compression, or heating, melting, etc. Heating, we could also have melting, or even boiling, right? You get the idea. We could also have dissolution, or a change in chemical composition, as in a chemical reaction. So that's the idea of what we call a process. The next term that we're going to talk about is the idea of work. And I'm sure you've heard it all along in your college careers thus far. Now, how do we define work? We said that work is equivalent to force times some distance. Mechanical energy transfer between the system and surroundings. We could also define it as some sort of mechanical energy transferred between the system and the surroundings. We could also describe it as an organized motion of molecules involved, and we represent it by symbol W. Right? So that's the idea of work. Now, work is done by the system if the mechanical energy is transferred from the system to the surroundings. All right, so that's very important. So let me repeat that. Work is done by the system if mechanical energy is transferred from the system to the surroundings. So let's give you an example. So let's say we have a torch. Let me go down a little bit. All right. So let's say that we have a gas torch or a lighter, and let's say this is the fire. And let's say you have something above it, and let's say this is gas, and let's say you have a block of mass M, right? And let's say the distance between here and here is what we call H. Now, the idea is that as the gas system, or in other words, the system is the gas, right? So as the gas or the system heats up, it expands and pushes the mass M in the surroundings, right? So in other words, we're actually doing work against gravity. So in this case, we're actually doing work against gravity. So in other words, then work, or what we call W, is negative. So therefore, work is equal to negative mg times h. And that is the formula that we would use. So let me rewrite this because this is ugly. But again, work is going to equal, in this case, negative mg times h. Now, again, we can also use another example saying that work is done by the system, or in other words, on the system. So this example right here was work is done by the system, right? So work is done by the system. In other words, the system here is gas, right? So we said that the gas was a system, and here work is done by the system. All right, and we said that work is done by the system if the mechanical energy is transferred from the system to the surroundings. Remember that we said that the block M is the surroundings, and we said that the system in this case is the gas, right? So as the lighter heats up, the system expands and pushes the mass up, right? So the mass is the surroundings. And so we're essentially doing work against gravity. In this case, work is equal to negative mgh. The second scenario is where work is done on, right? So this is not by now, but this is rather on the system. And we say it's done on the system if mechanical energy is transferred from the surroundings to the system. And we're going to do an example. So this could be something like, this. We have some sort of gas, and we have some sort of mass M, and it's pushing down. Maybe this is the height H. So if we add a mass, adding a mass M in the surroundings to the top of a piston, so let's say we're looking at a piston, and adding a mass M to the top of the piston actually compresses the gas. In this case, the gas is a system, right? So nothing changes from above. The gas is still a system. The mass is the surroundings. right? So now work is being done on the system. So the mass M, adding that mass M to the top of a piston, for example, compresses the gas, which is a system, and so we're doing work against the pressure of gas. So in other words, work now becomes positive. So work W is actually positive, and so this is going to equal to positive mg times h. So there are two different interesting cases between the idea of system, surroundings, and work. Now another term we need to talk about is the idea of energy. And energy is simply just the capacity to do work. So an example could be something like in a wound up spring, or something like a compressed gas, or a mixture of, maybe hydrogen gas and oxygen. Another term that we need to talk about in thermodynamics is the idea of heat. And heat is a form of energy. Right? We describe heat as a form of energy. We also say that heat is actually it's a random motion of molecules. So let me erase this. But it's a random motion of molecules involved. So heat is a random motion of molecules involved. Right? And the symbol, just like work we said was W, the symbol here for heat is actually Q. Right? So let's expand on the idea of heat. So the sign convention we actually use to describe heat. So if the thermal energy is actually transferred from the system to the surroundings. The thermal energy is transferred from the system to the surroundings, then the heat is actually, or heat, or Q, what we call, is actually negative. And we actually define that as an exothermic process. And the opposite is true, right? So if the thermal energy is transferred from the surroundings to the system, then the heat is positive. So if the thermal energy, and excuse me for my bad handwriting, is transferred from the surroundings now to the system, then the heat we define as Q, is actually positive. So note the difference. And this, ladies and gentlemen, is what we call an endothermic process. Now, let's talk about some terms here. So adiabatic is a term that we need to describe. And this is when no heat is transferred between system and surroundings. right? So in other words, we could say that this is maybe something like an insulated walls. Okay, so that's we define as an adiabatic process when no heat is transferred between the system and surroundings. We could also have an isothermal process, and that is where the temperature pretty much stays constant. So I'm just gonna say T for temperature of the system stays constant. Now, what about the Zeroth Law of Thermodynamics? The Zeroth Law of Thermodynamics. The Zeroth Law of Thermodynamics says that if an object A is in thermal equilibrium with object B, which is in thermal equilibrium with object C, then A is also in isothermal equilibrium with C. So let's represent that. The Zeroth Law of Thermodynamics says that if an object A is in thermal equilibrium with object B, I'm just going to write T for thermal equilibrium, which is in thermal equilibrium, now B now being in thermal equilibrium with object C, then what we're saying is that A must be in thermal equilibrium with object C. So that's what the Zeroth Law of Thermodynamics says. We also must describe what we call a state function. A state function is a variable whose value depends solely, right? So it depends solely on the current state of the system, right? So this may include examples. This may include examples such as T or P or V. Now, what's important to mention is that work and heat are actually not state functions. So that's important. So work and Q, heat, are not state functions. Last one that we need to describe is the idea of internal energy. And what do we want to talk about with respect to internal energy? Well, when work is done on a system, for example, like when a gas is compressed, its capacity to do work actually increases. In other words, that is the energy of the system actually has increased. Conversely, if a system does not work, its energy decreases. That's all we're saying. Right? So, in other words, the only thing we're saying is that when work is done on, right? So done on a system, its capacity to do work increases. Right? So its capacity to, excuse me. So its capacity to do work increases. Or in other words, what we're simply saying is that the energy of the system increases. And the opposite is true, right? If the system does work, its energy decreases. So if the system itself does work, the energy decreases. So we could say conversely, if the system itself does work, its energy decreases. Another point that we need to mention about internal energy is that when heat flows into a system, the energy of the system has increased, right? So to simplify it, we say that when heat, or Q, when heat flows into, right? So going into the system, its capacity to do work increases. Right? Or in other words, what we're saying is that the energy of the system has increased. And conversely, if the system does work, if the system actually does work, then its energy decreases. Right? Kind of the same point that we mentioned above, except we're doing with heat now. All right. The third thing I wanted to mention about internal energy is that if the total energy contained in the system, the total energy contained in a system is called its internal energy. All right. So the internal energy, which we've been religiously talking about, internal energy E is equal to the total energy contained in a system. Now, this energy may be stored by the system in the form of heat, molecular bonds, maybe something like as pressure in a gas, as gravitational potential energy, as torque in a spring. Like all these are examples where the energy may be stored by a system in the form of maybe heat or molecular bonds, etc. Okay? Fourth thing I want to mention about internal energy is that I'm just going to write IE for internal energy, is actually a state function. So the internal energy is a state function, and the symbol is actually U. Sometimes you may see it as E in older textbooks, right? But the symbol for internal energy is U, or you may see it sometimes as E in older textbooks. So now that we've learned all this pretty much vocabulary, essentially, we're now in a position to state the first law of thermodynamics. So what is the first law of thermodynamics? The first law of thermodynamics says that it essentially is a restatement of the law of conservation of energy. It can be stated in three ways, but equivalent. Right. So the first way we could say or state the first law of thermodynamics is that the energy of an isolated system is constant. So that's what the first law of thermodynamics says. Or we could say it in a second way, that energy cannot be destroyed. Any energy cannot be created or destroyed. Now, the second way is most commonly what you've probably heard, but again, remember we could state it in three different ways. The third way we could state it is that the total energy of the universe is actually constant. So the total energy of the universe is actually a constant. But we also need to mention that different forms of energy can be interconverted. So we need to also mention that different forms of energy can be interconverted. All right, so what do we mean? Let's look at an example. If I could have heat, and I could maybe transform heat into work if I use maybe a steam engine. So this may be something like a steam engine. I could also use gravitational potential energy, so I'm just gonna say GPE. I can use gravitational potential energy and create work if I maybe use something like a mill wheel, or I could actually use gravitational potential energy. This is kinetic energy, and this is electrical energy. I could probably use gravitational potential energy, convert it into electrical potential energy, using what we call a hydroelectric power. I could also convert electrical energy into light, and I could also convert chemical energy into light as well, maybe burning magnesium. Electrical energy is converted to light, maybe using something like a flashlight, or a flashlight as an example, right? So different forms. The idea here with doing this graph is that different forms of energy can be interconverted. So now that we've described the first law of thermodynamics, let's talk about the first law of thermodynamics in chemistry. So the first law of thermodynamics in chemistry. So in chemistry, we define the first law of thermodynamics as delta U is equal to Q plus W. Now we know that W is work, we know that Q is heat, and we know that delta U is a change in internal energy. Now the differential form in differential form, we actually say that du is equal to dq plus dw. So that's the differential form of the first law of thermodynamics. Now, remember we said that if heat is absorbed, by the system, it's an endothermic process. In other words, Q is actually positive. If heat is released, by the system, then Q is actually negative. It's an exothermic process. If work is done on the system, then W is actually positive. If work is done by the system, then W is actually negative. So we must keep these rules in mind. So if that is the case, the first law of thermodynamics was actually investigated by Joule, which is actually a British bureau, a student of actually Dalton. And he studied the interconversion of heat and work. And so if we look at the system that Joule studied, we essentially have this right here. We have this being water. He placed the thermometer into the water. And he had pretty much a blade connected by this anchor. And this was connected to a string connected to a block of mass M. And this was like a pulley essentially. And this whole area, let me go around it, this is actually an insulated vessel. So this was insulated. So this was an insulated vessel. So work is actually done, and I'm putting down the arrow, is that work is actually done by the falling weight. So the work done by the falling weight actually increases the temperature of the water. So this means that work and heat are different forms of the same thing, pretty much, namely energy, right? So this is all that I'm saying in this diagram, is that the work done by the falling weight actually increases the temperature of the water. So this essentially means that work, all right, so the main point is that work and the heat are different forms of the same thing, which is pretty much namely energy. This was discovered by Joule. Now, let's look at an example to kind of quell our knowledge on the idea of the first law of thermodynamics. So let's say that a battery-powered motor, a battery-powered motor lifts a weight expending 15 kilojoules of energy. Right? So a battery-powered motor lifts a weight and expending 15 kilojoules of energy E. During this process, the motor heats up and gives off an additional energy of 5 kilojoules of heat. Right? So during this process, the motor actually heats up. The motor actually heats up and gives off an additional 5 kilojoules of heat. The question is, what is actually the change in internal energy? So what is the change in internal energy E? That's the question. Well, the first thing we have to do is define the system. And the system in this problem is actually the motor contained in the battery. Now, if work is done by the system, it tells us that a battery powered lifts away, expending 15 kilojoules of energy, which means that it's giving off energy, or in other words, work is done by the system. So W in this case is actually negative 15 kilojoules, right? And this is work done by the system. What about the heat? Q in this case is actually negative 5, right? Because the heat is released from the system at this point, right? So it did say that during this process, the motor heats up and gives off an additional 5 kilojoules of heat. So we have to, our sign convention is really important here because it gives off an additional 5 kilojoules of heat. Q is defined from heat, and so it must be negative because the heat is released from the system. So because we've now defined our two parameters, we could therefore say that delta U is equal to Q plus W. In this case, they're asking for the internal energy, so delta U is going to be equal to negative 5 plus negative 15, and that is negative 20 kilojoules. So that would be the answer for this problem. So if you look at it, really all this energy is lost from the battery, which is a reservoir of energy, right? So the battery is a reservoir of energy, and we're really saying that all this energy is lost from the battery in the problem, right? So the motor simply acted as a conduit or maybe a converter for the energy transforming electrical energy into mechanical work and heat. So let's look at a couple scenarios. Let's say that we have a box, and let me actually draw this differently. So let's say we have a box, and let's say that this is our motor connected to maybe a battery. And this is the battery, right? So there's our motor. I'm going to write B for battery. The system in this case, the system S, I'm going to represent as S is equal to the motor M plus the battery B. If you look at another example, here's my motor. It is connected to a battery. And the battery is B. And here's the box. So in this case, the system S is just equal to the battery. Whatever is in the box would be your system. Now delta U on the left in this case is equal to negative 20 kilojoules, which is what we calculated above. The system is still equal to the battery in this example, so delta U is still equivalent to negative 20 kilojoules. Now, what about this last example? If we had, here's our motor, and it is connected to a battery. And let's say that now the motor is just our system. So S is equal to M. The change in internal energy for this will actually be 0 kilojoules. So as long as the system is composed of the battery, or internal energy or change in internal energy is going to be negative 20 kilojoules, which is what we calculated. If the system is only the motor, then that in fact is actually 0 kilojoules. Now let's transfer energy to what we call pressure, volume, work. All right, so let's look at the idea of what we call pressure, volume, work. So let's say that we have some sort of gas at pressure P. So this is gas at pressure P. And let's say that this is some height h. Let's say that we have some sort of force external. And let's say that this is some sort of area A. The work involved in expanding or compressing a gas, in this case, suppose the piston. So in this case, we're looking at a piston. Right? So let's say this is a piston. So the work involved in expanding or compressing a gas, suppose the area of A moves up against the constant external force. Right? So let's relive a scenario. Suppose the piston of area A actually moves up against, let me respell against because this is terrible. Against the constant external force. Then what would we actually be saying? In this case, then the work is then equivalent to negative the force external times h. And we could also rewrite this as negative the force external divided by the area times h times a. The only thing I did was just rewrite that formula. If you cancel it, the a's out, you pretty much get the same thing. Or we could actually rewrite this formula as negative pressure external, because the force over area is what we define as pressure times the change in volume, which is HA. Now, for very infinitesimally changes in volume, so small changes in volume, so for very small changes in volume, we actually can write this formula a little bit different. We could then say in a differential form that dW is equal to negative P external, this should be a T, equal to negative P external dV. So in this, for infinitesimally small changes in volume, that formula, this formula would actually suffice. Now let's change our energy, or let's change our focus to know what we call gas expansions. So the first one we want to talk about is the idea of a free expansion. So a free expansion is pretty much an expansion of gas against zero pressure. Right? So free expansion is an expansion of gas against zero pressure. So in other words, the pressure external must be equal to zero. In other words, it's constant. Now the work is equal to negative the pressure external times the volume. So in this case, if the pressure external is zero, that means that the work is actually zero for a gas expansion. Very critical. Now the second one that we want to talk about is the idea of expansion against constant pressure. So when we talk about the expansion against constant pressure, here the pressure external is actually a constant. So it is actually a non-zero number. So it is non-zero. Right? So in this case, if we want to look at the derivative, we could then say that the work is equal to the integral from V initial to V final, and the integral must be negative of P external dV. Right? Now, since the pressure is constant, we could actually pull it out of the integral, and this would put us at negative P external times integral of from V initial to V final dV, and that is essentially also equivalent to negative P external times V final minus V initial. And this is dV. So this would be dV. Sorry for my terrible handwriting. Right? Or we could simply define the work for an expansion against constant pressure as negative P external times delta V. So the work for a free expansion is 0, whereas the work for an expansion against constant pressure is negative P external delta V. Now, we should mention some things about what we call reversible processes. Now, reversible processes, or actually idealized processes, they proceed in infinitesimally steps or small steps. They proceed in infinitesimally steps. The system reestablishes equilibrium after each steps. There's no friction or no eddies / turbulence. Eddies are the same thing as turbulence, right? Internal and external pressures balance during the entire process. Any changes in the system and surroundings can be reversed in infinitesimally steps. The system and surroundings can also both be restored to their initial conditions, right? We also may be visualized as a very slow process. So these are just characteristics of a reversible process, right? So these may also be visualized right? The systems and surroundings are actually at equilibrium throughout the process. So these are some characteristics of a reversible process. Now, if any of these conditions that we mentioned above, some of which I did not write down, are actually not met, the process is said to be irreversible. Right? And these are some characteristics for irreversible processes. Right? So all real processes are actually irreversible. Right? So all real processes are irreversible. We also said that it's possible to approach reversibility by carrying out processes infinitesimally small, right? And then in a reversible process, there's always some loss in energy as heat, right? So there's always some loss of energy as heat, or it could be some sort of frictional loss or viscous drag. maybe some sound, etc. So let's continue on our gas expansion. We spoke about a reversible, we spoke about the two gas expansion that we spoke about was free expansion and the expansion against constant pressure, where we said that for free expansion, the work is actually zero. For expansion against constant pressure, the work is actually negative P delta V, and the pressure is actually the external pressure. And we're going to continue on the third one, which is actually a reversible expansion. Right? So the third one is actually a reversible expansion. So for reversible expansion, we say that the formula, or dW now, is actually equal to negative P external dV. So that is the formula. Now for a reversible process, we must mention that for all times, the pressure external is equal to the actual pressure at all times. So if that is the case, then we can then say that dW is equal to negative P dV, since the pressure external is equal to P. So the only thing I did from above was just substitute pressure external for P. Or we could actually say that the work is equivalent to negative the integral from V initial to V final of P dV. Now we could also expand this formula, and so this formula is very important to know, but we could also expand it for an ideal gas. So we could say that this is equivalent to negative the integral from volume initial to volume final of nRT over V dV. And this formula is what we define is for an ideal gas. So that is the work for a reversible gas expansion. The fourth one that we want to talk about is the idea of isothermal reversible expansion. So an isothermal reversible expansion says that the reversible component comes from the fact that the work is actually equivalent to negative the integral from V initial to V final of P dV. And we did say that for an ideal gas, the work W is equivalent to negative the integral from V initial to V final of nRT over V dV, right? Now the isothermal component comes from the fact that temperature is constant. So the isothermal component comes from the fact that T is actually constant. So therefore, if T is constant, we could actually rewrite the equation for work as W being negative RT, because this is constant, negative RT is actually constant, times the integral from V initial to V final of 1 over V dV. And this is equivalent to negative nRT times the natural log ln V final minus ln V initial. Or, excuse me, or we could rewrite this whole equation as the work being negative nRT ln of V final over V initial. And that is the work for a isothermal reversible expansion. Right? So if we look at a graph of this process, we may have V on the x-axis and pressure P on the y-axis. And we may have some sort of V initial, and we may have some sort of volume final. And this may be your V initial, this may be your V final. This is all shaded. And this is actually what we call an ideal gas isotherm. So at constant temperature T, the area under the curve or the shaded regions actually represent the work done in an isothermal reversible expansion, right? So this area shaded is actually W, or the work done in an isothermal expansion. The last one that we want to look at is constant volume process. So as this gas expansion suggests, the volume is constant. So in other words, dV is equivalent to 0. Thus, we could actually say then that dW is equal to negative P external dV, and that is equivalent to 0. And we must state for constant volume processes, W work is actually equivalent to 0. Now, since there's something else that we could add on to this, remember that, so we could actually recall that the first law of thermodynamics says that delta U, excuse me, not W, but delta U is equivalent to Q plus W. Now, since for a constant volume process, W is equal to 0, as we just said above, then for a constant volume process, delta U is actually equivalent to Q. All right, and this is at constant volume. So in other words, the change in internal energy of the system depends solely on the heat absorbed or released. Right, this application at this applies to stuff like bomb calorimetry or calculating the heats of reactions. Right. So again, that is the end of the lecture, ladies and gentlemen.